Hello everyone, welcome to digital communication, that pulse amplitude modulation time division multiplexing system in unit 4. Here we have the figure. There are two rotary switches. One is commutator. In the transmitter side we have a rotary switch, that is commutator. In the receiver side we have a again rotary switch, that is decommutator. Transmitter side rotary switch is called as commutator and receiver side rotary switch is called decommutator. We already know that multiplexer means many signals are combined together and transmit through a single channel, the transmission system. And we have the synchronization between these two rotary switches, that is commutator and the decommutator. What signal is transmits in the transmitter. Here we have x1, x2, x3, x4. Four different signals are there. That same particular signal, if x1 is transmitted by the commutator, the decommutator should select x1 in the receiver only. Then only we have the synchronization, and then only it is possible to receive the actual signal. Here this figure shows the block diagram of four channel. There are four channels, x1, x2, x3, x4. Four channel pulse amplitude modulation time division multiplexing system, PAM TDM. You already know that pulse amplitude modulation. Here continuous pulses are converted into a continuous waveforms are converted into a pulses. That pulses amplitude is changes, and in this we have the sampling theorem, that is sampling frequency fs should be greater than or equals to 2 fm. That is the required condition to have the minimum distortion at the receiver. Fs should be greater than or equals to 2 fm. Okay. Here we have pulse amplitude modulation time division multiplexing. The rotary switch samples one particular signal at a time. For a particular time interval, it samples one signal, then it goes to second signal, third signal, fourth signal. Again, it comes to the first signal. The cycle is repeats. Similarly, here also the same signal is received by the decommutator. And here we have the baseband signals, that is x1, x2, x3, x4 baseband signals. We have four low pass filters to pass that particular signals. Here x1 passes the one particular signal. This x2 signal is passes through one particular low pass filter. Like this, the low pass filter has a particular cutoff frequency, and these all signals are baseband signals. Baseband signals means you already know that the basic modulating signals. Here the switch makes a fs revolutions. The switch makes a fs revolutions per second. Fs is sampling rate, the switch rotation rate, fs revolutions per second, and in one rotation it extracts one sample from each input during revolution. See here x1, x2, x3, x4. One frame is completed. Then again it starts x1, x2, x3, x4. The output of the switch is pulse amplitude modulation waveform containing a samples of the input signal periodically interlaced in time. Here actually it is an electronic switch. Field effect transistors are used. Here that Field effect transistors are controlled by digital circuits that sets the sampling intervals and pulse rate, because we need the condition Fs should be greater than or equals to 2Fx. Fx is baseband signal. The period of time during which all the channels in a PAM system are sampled once is called frame. Here, one rotation, completion of one rotation is called as one frame. So here we consider that the period of time during which all channels in a PAM system are sampled once is called frame. Here this indicates the transmitter part. At the receiver, that sampled signals are received and they are separated by a switch. That switch is called as distributor or decommutator. The receiver side rotary switch is called as what? Decommutator. The samples from each channel are filtered or reproduced the original message signal by using again filter here. Here we use low pass filters 1, 2, 3, 4 for signals x1, x2, x3, x4. What signals are transmitted here? That same signals are received by the receiver by the same position, and it goes to the particular filter, and at the output of that filter we have the original signal. The rotary switches at the transmitter and the receiver are usually electronic circuits that are carefully synchronized. If you have the synchronization, then only it is possible to receive that particular signal at the receiver. Synchronizing is perhaps the most critical aspects of TDM. If there is no synchronization, it is not possible to receive the actual signal. Demultiplexing PAM signal requires some means of synchronization to ensure the matching clock frequency. If suppose you consider that it rotates in x2 and this receives the x4, then there is no synchronization. The signal mismatching is occurs. So in PAM TDM system, we need the exact synchronization between the commutator and the decommutator. Here we have a transmission bandwidth. What bandwidth is required in PAM TDM? Here you consider this n is equal to number of multiplexer signals. In this example, that n is equal to how much? 4. N is equal to 4. And fx is message signal bandwidth. That is the baseband signal. Message signal bandwidth is considered as what? Fx. According to sampling theorem, that sampling rate fs should be greater than or equals to 2 times that of fx. Here fs is sampling rate, and reciprocal of fx is 1 divided by fs is nothing but what? Ts, that is time interval. Ts is equal to 1 divided by fs, that is equals to sampling interval. You already know that frequency and time are inversely proportional. And also you know the condition according to sampling theorem, sampling frequency fs should be greater than or equals to 2fx. If fx equals to 2 kilohertz, then fs should be greater than 4 kilohertz or equals to 4 kilohertz. Then only it is possible to have the distortion free output, or we can reconstruct the original signal with a minimum distortion. You already know that fs equals to 2fx is Nyquist rate. If fs is greater than or equals to 2fx, then there is no aliasing effect, there is no distortion, there is no interference. Therefore, the time interval between the successive samples from any one input, fs is greater than or equals to 2fx, and you know that ts is 1 by fs. ts is lesser than or equals to 1 by Fs, or you know the condition Fs is greater than 2Fx, therefore Ts is less than or equals to 1 by 2Fx. Instead of Fs you substitute Fx, 2Fx, right? So Ts is less than or equals to 1 by 2Fx. The time interval Ts contains one sample from each input. The time interval Ts contains one sample from each input. This time interval is called frame. To complete one cycle, how much time it takes, that is called Ts, and that is called as what? Frame. One frame. To complete one rotation, how much time it takes, that is called as one frame. Here n input channels. In this example we have a 4 input channels, x1, x2, x3, x4. Then to complete, or it samples one particular signal, one channel, for how much time interval? To complete one rotation it takes Ts. For example, if you consider that Ts equals to 1 millisecond and there are 4 samples, to complete one sample or sample to sample spacing is equal to what? 1 millisecond divided by 4. It becomes 0.25 milliseconds. Correct? Here sample to sample spacing is equal to time required to complete one rotation, that is sampling time Ts, divided by n. N is number of channels. And number of pulses per second or pulse frequency is given by number of pulses per second or pulse frequency is given by, in 1 second how many pulses it takes is calculated by what? 1 divided by sample to sample spacing. Sample to sample spacing means to complete one pulse, that is one channel, how much time it takes, that is sample to sample spacing, that is equals to Ts divided by n. To complete one, suppose in this example, to complete one channel or one sample it takes 0.25 milliseconds. Then in 1 second how much samples it takes, number of pulses it takes in 1 second, that is calculated by what? Number of pulses per second is equal to 1 divided by sample to sample spacing. Number of pulses per second is equal to 1 divided by sample to sample spacing. Here 1 divided by time interval to complete one channel is equal to number of pulses per second. You know that sample to sample spacing is equal to Ts by n. You substitute this value in this equation. What it becomes? Number of pulses per second is equal to 1 divided by Ts by n. 1 divided by Ts by n. Then it comes to n comes to numerator. N divided by Ts. Number of pulses per second is equal to n by Ts. That's equals to n into Fs, because Ts is equal to what? 1 by Fs. That Fs comes to numerator. Therefore, number of pulses per second is equal to what? N into Fs. N is number of channels. F is number of pulses per second. Clear? Number of pulses per second is also called signaling rate. This number of pulses per second, N into Fs, is also called as what? Signaling rate. signaling rate R is equal to N into Fs. Fs is sampling frequency and N is number of channels. And you know that Fs is equal to or greater than 2Fx according to sampling theorem. Therefore, the sampling rate should be the signaling rate should be greater than or equals to 2n into fx, because fs equals to 2fx. Signaling rate, when we want to transfer that signals through a channel, that channel signaling rate should be greater than or equals to 2n into fx. Then we have the distortion free output at the receiver. Then bandwidth, you already know that bandwidth is equal to half of the signaling rate. Bandwidth is equal to what? R by 2. What it becomes? B is equal to R divided by 2. B is equal to R divided by 2. What it becomes? R is equal to 2n into fx. 2n into fx divided by 2. What it becomes? N into fx. Therefore, the bandwidth Bt is equal to n into fx. It shows that if there are n channels, in this example 4 channels in TDM, which are band limited to fx hertz, each band frequency is equal to fx hertz, then minimum bandwidth of the transmission channel will be equals to n into fx. For example, here you consider that fx is equal to 2 kilohertz, number of channels is equal to 4, then required bandwidth is equal to how much? 8 kilohertz. N into fx. In the PAM TDM system, the required bandwidth Bt is equal to N into fx. Fx is band limited frequency, that is in kilohertz, and N is number of channels. Then it indicates Bt is equal to N into fx. N is number of channels. In this example, N is equal to 4. Suppose, for example, you consider that fx is equal to 2 kilohertz, then what it becomes? N 4, fx is 2, it becomes 8 kilohertz. Clear? It shows that there are n channels in TDM which are band limited to fx hertz, then number of bandwidth of the transmission channel will be equals to n into fx. Clear? Next, synchronization. We need the synchronization between the commutator and the decommutator. To have that synchronization, we use the marker pulse in PAM TDM system. Marker pulses for synchronization in TDM. When it completes one frame, after the completion of one frame, we use one marker pulse. Otherwise, the second frame signal may be interfere with the first frame. To separate the first frame and the second frame, we use a marker pulse. See here, the first frame ends at this point, then second frame starts at this point. Here we have a one marker pulse. That marker pulse is not connected with this frame. One frame means here the number of channel signals, that is number of channels or number of signals, number of samples. After that, one marker pulse. This is one frame. Then second frame starts. When we have this marker pulse between the previous frame and the next frame, then we have the synchronization. By that marker pulse, we can identify that the previous frame is ends. After that, the second frame starts. When we have the synchronization, then it is possible to reconstruct the original signal at the receiver. In the TDM system, we need this synchronization. Okay, thank you.